See basically how to create a super hydrophobic surface through combination of texture and chemistry. Okay, so the model we have on the left is called the Wenzel model. So here we have a drop penetrating the roughness elements. We recycle our picture. Let's put a rough surface down. The change in wetting energy associated with this motion by advancing an amount dx. So again, R is our roughness element, so it's our roughness parameter. So the total energy divided, or sorry, the total surface divided by the planar surface. And theta star is again our effective contact angle on the rough surface. So note, if R is equal to 1, that is to say we have a smooth surface, we retain Young's law. For the equilibrium contact angle. But if R is greater than 1, then we get cos theta star is greater than cos of theta equilibrium by an amount R. Okay, so this is saying that it can get very large. So we can, in principle, so we can amplify the wetting tendencies of the surface via roughness. So for example, if we have a hydrophobic surface, so imagine we have a waxy surface as we have oftentimes in nature. So we have a waxy surface for which equilibrium contact angle is greater than pi by 2. So cos theta E is less than 0. Then you get the theta star is much greater than pi by 2 for large R. Okay, but this is part of the story, so we can say that we can get this equilibrium contact angle up very high, but that's only part of the picture. For something to be waterproof, the drop has to roll off when it hits. Now, unfortunately, when you're in the Wenzel state, the contact angle hysteresis actually increases. Okay, so the other thing to note, so this is saying when we're in this Wenzel state, there's something which starts like that. We roughen it. It's going to become even more hydrophobic. We also know that if this equilibrium value is less than our theta c, so this is the wicking angle, which depends on surface texture. then we get generally wicking, complete wetting, right? So if this contact angle is small, then the thing is just going to spread into a puddle, right? Okay, so this is saying we drop here. If the contact angle, basic contact angle is small enough, it's going to basically spread. It's going to wick, and so basically vanish. Okay, and the other. Okay, and so the one restriction of the Wenzel model is if we make, so this is all fine in practice, we can take the limit of r going to infinity, but in reality there's a critical r at which this state no longer exists, and it just becomes too energetically costly to wet all of the surface, and so you go into this state. Okay, in the inclusions. So as to say, in the roughness element. So you basically go from this Wenzel case to the Cassie state as the roughness increases. Okay. So when this happens, we switch into the Cassie state, and we can also describe the energetics here. So here the drop sits on the roughness elements. So we can think of them as pillars or islands. Okay, so here we imagine trying to do a slightly more regular array. So let's imagine pillars. Then we have our theta star. So it's a fluid phase, vapor, solid. So as this thing advances, find them out, dx. And we can also get the change in. So we again want to get this. We want to get a similar relation between the effective contact angle theta star and the surface topography and the equilibrium contact angle theta e. Okay, so the change. So the change in surface energy associated with this interface advancing an amount dx. So again, we're imagining this sort of island scenario. Okay, so there's a change because you're basically creating three interfaces. And so whether or not this is energetically favorable depends on the topography. So we get an equilibrium when we set this equal to 0. So this gives us an expression for theta star in terms of the topography and the equilibrium contact angle. Okay, so we can see immediately, so this is basically this is again the area of the tops of the pillars to the base. So basically, if you imagine these are pins, right, then this is going to go to 0. Okay, this goes to 0, and so you get cos theta star is -1, which says the contact angle is going to 180, right, which is the optimal in is the highest possible contact angle. Okay, so note. So the pillar density phi s goes to 0, so then it's basically sitting on so theta star is pi. So my friend David Carré came up with a good name for these. For drops in this state, these are called says they're in a fakir state. Because a fakir is the Indian gentleman sitting on a bed of nails, right? And it's this fakir state where one is, which is desirable for water repellency. Because the drop will simply roll. So it's being suspended on a bed of nails, right? So if this is our substrate, we have our bed of nails, and the drop is really sitting there with contact angle of about 180 degrees. Okay, and this is a favorable state. So this is an independent fact, but this is why, so you can't see from the energetics, but this has much lower contact angle hysteresis than this. So these guys won't stick. So actually, going into the Wenzel state, you actually increase contact angle hysteresis relative to that on a smooth surface. But you decrease it tremendously. You can get, say, in a Cassie state. Okay. So maintaining this Cassie state is the key for water repellency. Okay, so let's try and predict the crossover from one to the other. So when are we going to naturally go from this? How can we justify this in terms of energetics? Okay, so in order for the energy of the Wenzel state to be less than the energy of the Cassie state, cos theta star. Okay, so our requirement depends on both the equilibrium contact angle and the surface topography. And this is, remember, this is our wicking angle. Okay, i.e., if we're less than this wicking angle, then it's going to go, it's happy to be in the Wenzel state, right? Okay, and this is simply because we know below this wicking angle, you put a drop down, the fluid's going to wants to go spontaneously outwards, right? So the Cassie state is not going to be achieved. The fluid wants to wet the rough solid. Okay, so we've spoken about the Cassie state. This Cassie state which I've drawn here, which is the Fakir state where you have air underneath it. You can also have a wet Cassie state. So if we do have the situation where the fluid wicks along the bottom, then you can also calculate the equilibrium contact angle if you're in a Cassie state. Right? So you can say, let's call this a wet Cassie state. So this is, you expect to arise if the fluid is if the surface is hydrophilic, say if you're using water. Okay, and so this is generally, and this is worth seeing because you can basically have a patterned surface with any sort of chemical heterogeneity, and this is basically how you treat it. So imagine you have two phases. So you have a tiled surface. So you have phase 1 and phase 2, and you want to know how a water drop spreads on it. So this is how you can do it in general. So think of this as a drop on a chemically heterogeneous substrate. So imagine we have now a tiled surface with two phases. And you can imagine, so this is the most general case of rough surface. So it can be the fluid of the drop, it can be air, and you can have the substrate, and you can have two completely different chemicals. So so let's so there's two species. One with area fraction F1 and equilibrium contact angle theta 1. So let's call this F1. So that's going to be the shaded things, and this is going to be F2. So these are the two areal fractions. And here we have theta 1, and here, say, theta 2. Okay. So the energy variation, if we have an interface, so again, in looking at the effective contact angle, you're averaging over these heterogeneities. Okay? The energy variation associated with the moving contact line Okay, so again we have to put subscript on things now, because we have three phases really. Okay, and so we get equilibrium. Okay, so we see that it's a weighted mean. And it's weighted with the areal fraction. Okay? Okay, so we can look at special case. And we're going to see this popping out, so we can look at the case of hydrophobic. So we can set one of the phases equal to air, and then we'll get our previous result. Okay, so first we look at the hydrophobic case. Okay, so let's go back to our Fakir case. So we just have the solid, which has theta 1 equals theta E, and then F1 is given by Vs. So So that's the first phase, and the second phase is air. So we can characterize F1 and F2 in terms of this island parameter. So we have our previous result, cos theta star. Okay, so again, so the Winslow state is energetically favorable. When cos theta c is less than cos theta e is less than 0. So we're going to basically do a whole map of the dependence of this angle on the equilibrium contact angle as a function of the roughness. So in all of the possible cases, which is why we're doing things in all generality. E Okay. And again, theta c okay, so we've seen this case already. Now if we look at the hydrophilic case, okay, so here so this is basically our wet Cassie state. So the two phases are the solid. And the fluid. Okay, so this is basically, we're looking at the energetics of a drop wetting wet roughened surface, right? So this is our theta 2 equals 0. There's no contact angle between water and water. And F2 is 1 minus Vs. So this is again the wet Cassie state. Okay, so the picture here, Cassie or Cassie Baxter, is this. So imagining that this fluid front, equilibrium potential advancing. So these are full of fluid. Right, so this is the same. Let's do this. They're all, so the puddles are already full of the fluid. Right? So this is wet Cassie. Okay, so energy variation in this wet Cassie state so this is going to be So this is going to move again if we exceed this wicking angle. Okay, so okay, so we can now actually summarize the entire regime diagram. So write out cos theta star as a function of cos theta e in these various regimes. Okay, so if we're hydrophobic, so this is cos theta e, this is cos theta star. So if we're hydrophobic, hydrophilic, okay, we've already done the hydrophobic case and we know that it should look like this. You basically have, this goes linearly with this and the slope is r. So it looks like this, but then there's a crossover value which is cos theta c, at which the slope changes. And so this then goes I don't like that plot too. Let me try that again. Okay. So this was the form of our cat. So this is when we're in a Cassie state. This is again the hydrophobic case. So this is the Fakir state, and then but in that takes over this critical angle theta c. But one also has the possibility of a Wenzel state. Yeah, yeah. So you get to this basically this wicking angle. One has the possibility of this. Now it turns out that this is you can also get a metastable Cassie state. So if you start in a Cassie state, it will tend to stay in a Cassie state. If you give it a big kick, it can go into a Wenzel state, and that will actually be energetically lower, but it needs a real kick to get into it. Right? So you can have these metastable Cassie state living on here.
But forever? I mean, the square, would it sort of die off, fade out something?
It will,
even without the kick? You
but
understand what I'm saying? Like,
yeah.
It goes and then sort of fades out.
Yeah, it's not entirely clear because it's you can ask how the fluid knows that there is an energetic, like if it's in an equilibrium state, it's an unstable one if given a sufficiently large kick. So presumably it gets more and more unstable as you get
Small,
as you move from the edge.
perturbations, just like.
Yeah. Okay, and so.
How old is all this, John?
Yep.
How old is all that? I never heard of Cassie.
So this is actually pretty new. So David Carré has done a lot of this. Rationalizing this plot is all like certainly the last 10 years.
And these guys, Cassie and.
Yeah, so they did mostly observational things and a little bit of surface dynamics, but the experiments have been done quite recently, last 10 years I'd say. But these guys, Wenzel and Cassie, those are like in the 60s, 70s.
Equating these things is all from the 60s, 70s?
Yeah.
And is there like a book one finds things like this?
Yeah, Degen's book with Carré. Yeah.
Which is from which year?
That's the last 5 years.
Oh, so it's recent, right?
Yeah.
It's been on my textbooks.
Yeah. Okay, and so we've got this result here. So here we're looking at the wet case, and so again we have this situation, this critical transition between Wenzel and Cassie. So we can have a wet, so this is in the hydrophilic case, so now we can have the wet Cassie state. And this is the Wenzel state. And again, we have this crossover at this critical valley. And so again, in reality, what one actually sees is something which looks kind of like this. Because this metastable Cassie state tends to live, but this is pretty much what's observed. Okay, and so the question is, so is a surface actually? So you were asking about the history, and history is quite interesting. So who first cared about this problem? There was people who were designing insecticides, right? So they want to design poisons that would kill insects but not stick to the plant, so they wouldn't kill the plants, right? So insecticides. And it's actually rather a subtle problem because most insects and plants, they've co-evolved. So they'll oftentimes mimic each other's surface coating. It's not clear whether it's through gene transfer. It's kind of a horizontal, they call it horizontal gene transfer. It was very interesting. The possibility of you are what you eat. But you literally get genes from your... because the eggs will hatch, for example, inside plants. So there's the possibility that there's some genetic transfer. But in any case, they tend to copy each other's surface coating. So if you zoom in on a microscope and look at the surface texture of a bug, then it oftentimes looks very much like the surface texture of the plant that it feeds on. Right? And so you then have to design something which is going to stick to one thing and not the other. So it's really quite hard. Okay, and then... And so in a booming industry now is designing super hydrophobic and super oleophobic. So you can ask the same questions, it's the same formulation. We've been talking specifically about water, but you can also think of oil. And there are many situations where you don't want oil to wet something. So Teflon is an example of something which is very rough on a microscale, and so things don't stick to it. Oleophobic surfaces, and so they do this. Again, it's always via a combination of chemistry and texture. Okay, and so these are some recently designed super hydrophobic surfaces, and actually one guy came. It's like one of the useful applications of fractals is somebody designed a fractal-like surface. So basically, again, there's going to be a huge energetic cost because there's a very large surface area if you have something incredibly rough. But these are some surfaces, and again, you can increase the contact angle enormously by making them very rough. So again, just increasing the energetic cost of wetting. And again, this is possible now. So we have some scale bars here. Yeah, so this is 50 microns. So you have texture down to about 50 microns. And yeah, so this gives you an idea. So these are fractal texturing. So this is Herminghaus. But here you have what the wetting is on a smooth surface and what it is on a rough surface. So you see it's an enormous difference. And here you can see the nature of the texture. So you have things down to texture down to 3 microns. Yeah. Yeah. So zoom, 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 and you get texture basically down to 3 microns. And this is, again, they're taking their lead from plants. If you have something with the basic, a requirement here is that this always be greater than pi by 2, right? Because it has to be hydrophobic. But once it is, then roughening it is going to allow you to go all the way up here. And so now, this is the most effectively a perfectly hydrophobic surface. So not only do you increase the contact angle, but you eliminate contact angle hysteresis. So this is a guy, McCarthy, who I think is at UMass Amherst, but he's designed this. This is like the ultimate surface. So basically, these are sort of. I'm not sure what the chemistry is, but you can see the texture. It's almost moss-like, right? There's an enormous cost of wetting, and the texture's down to 50 nanometers. But a drop will stick to this stuff and just roll. Right? And there are other things that you can do. You can you can make a directional surface by texturing. So if you put a drop on a grating, then the drop will roll with relative ease in that direction, but not across the grating. Okay, and so this is actually used by as we'll see later. I'll give a course on a lecture on biology, but this is used by water-walking insects. They actually have texture on their legs, which allows them to glide very easily in one direction, but generate large forces while striking in the other. And so, and it's basically, you can understand how things work in terms of contact angle histories. So here there's going to be a lot of pinning as the thing advances, right? Because you're going to have all of these very corrugated contact line here. There's very little energetic cost to sliding. Okay, and so here, this is actually inspired by our thing on the bugs. So we predicted that you could make a unidirectional surface. So this guy basically has texture, which is pointing in this direction. Okay, and this has just texture up and down, and you basically vibrate. So this is a directional surface, is a non-directional surface, but they're both water repellent. So we have the same contact angle, but this one's tilted, and so you vibrate the thing, and it has a tendency to move in one direction. So you can simply use vibration and texture to drive drops around on a micro scale. Okay, so that's it for that. And so then the question is, when can you retain a water repellent state? And that's simply a question of the impregnation pressure not being too large. So we've seen that water repellency requires that we stay in a Cassie state, and so that's just saying that the largest pressures around, so let's call them impregnation pressures, these have to be small relative to the curvature pressures generated by the texture. Okay, so let's look at a few examples. So if we have just a drop sitting on a rough solid, okay, so if it's a small drop, it's going to look like this. So what's the pressure here? This is atmospheric. It's going to be P naught plus 2 sigma over R, right? So that's the pressure difference. That also, so that's the pressure. This is trying to drive things into the texture, right? And so you're going to be fine. So if you zoom in here, notice that this curvature has to be the same as this curvature, right? Because the pressure difference, this is connected to air, the atmosphere, then it has the same pressure. So the curvature here always has to be the same as the curvature along the drop, right? So if you zoom in, let's do a slightly better job than that. And our interface is going to look like this. And we know what its curvature is. The deflection here is delta. This is L. So for static drop, so the radius of curvature is going to be, so from this picture you can see what this curvature is going to be, order delta over L squared. So this tells us what the so you can convince yourself of this, right? We have to get a curvature from this shape, right? It's basically, it's got to have a scale of 1 over length. You can convince yourself of that. Just remember what the curvature of, it's hxx, right? If you have a curve which is h to the function of x. So this is basically hxx, right? Okay, so a scaling argument version of it. Okay, and so interface will touch down if delta is greater than, so this is the pillar height now. Delta is greater than h. So L squared over h is greater, so L squared over r.
John,
hold on.
These are for small droplets, so that means no gravity, is that it?
Yeah, that's right.
It's very small
That's right.
droplets.
Exactly.
If there was gravity, there would
Exactly.
be the rate, right?
Yeah, but there are a lot of situations, again, we're small relative to the capillary length. So you're, right? Then this is going to be correct. So this is this, and so i.e. r less than L squared over h. So we're going to have longer pillars are going to be give us a more hydrophobic surface. So that's going to assist in water repellency. So we're basically asking the question, when is this thing going to touch down?
You're considering structure, right?
No, just, well, it doesn't really matter. No, it's a 2D argument, but it carries over to 3D. And then, so that's a first. So a second one, a little simpler. If you just have drop impact. So we have some rough surface here, and we have a drop coming down. It's coming down at a speed u. Then we expect the characteristic pressure is going to be rho u squared. So this is going to be so that's what we expect to be the impregnation pressure, right? So the curvature generated here has to exceed this pressure, right, in order to maintain a water repellent state. And so this is a big question when trying to rationalize the texture of plants. Why does it go? What sets the minimum scale? And the largest pressure they have to worry about typically, and this is true for water-walking insects and many insects, the largest pressure they ever have to face is the dynamic pressure of a raindrop impact. Okay? So they basically will design themselves to be able to maintain their water repellency in the presence of these sorts of pressures. And worse yet, when a raindrop hits, there can actually be shocks within the raindrop. So the characteristic pressure is no longer rho u squared, but rho u times the speed of sound in water, which is an order of magnitude higher. Little known fact, but it's like a water. You've heard of the water hammer effect. But you can basically get very large pressures, which can then prompt wetting. Okay, and the third, simplest one, if you're want to design a water repellent boat, and there are many reasons to do so. In particular, you have an air layer. You basically have a trapped air layer on the boat, and so you get greatly reduced drag. Then this is your boat. Then the characteristic pressure you're going to get is just going to be rho gz, right? Delta P rho gz. Right? So you basically have to design so that the roughness elements are sufficiently small, or this is true also for underwater. If you made one of these underwater breathing devices, which I mentioned earlier, you have to make the roughness small enough that it resists the impregnation pressure, which is here, that. Okay? Okay, and so I think that's all for today. I think we have a couple of pictures of. Exactly. Who cares about surface tension? These guys do, right? I mean, all they have to do is access the drop, and the curvature pressure just feeds them, right? So they have to punch a hole in the drop. Yeah. So here's some examples of drop impact. So again, the question is, does it stick or does it bounce? And that's going to depend on whether the dynamic pressure is large enough to impregnate the roughness. And here you see that it does, so the thing will stick. And that, if that's your Gore-Tex jacket, you're going to take it back. You're going to complain. Right? And then...
It's an amazing video. It doesn't pop. It forms like crazy. It doesn't pop.
And so, but if you've got a good vortex jacket, your raindrop impact will look something more like this, right? What's that? Yeah. So here again, it's just a question of so there will be basically a wetting speed, right? A speed at which a drop will wet a surface. And in nature, for plants and insects, the speed they have to worry about is the raindrop impact speed, which is about 10 meters per second.
So that scale you put there, which is rho v times the speed of sound.
Yeah.
That's because when there's an impact, there's like
Shock.
but it has to do with acoustic waves. Or
It's compression at the impact. And so, so that's the wonderful world of water repellency. And again, one learns, man has learned a great deal by looking at nature's designs. I think it's water. I think it's water on a super hydrophobic surface. Yeah. Yeah, you can see it's small because, and then so here another example. So you can, if you make these things super hydrophobic, then vibration will easily move things around, and you can even, chemical gradients will move drops. Wait, what was the? Oh, this is the example. So we'll do I'll show you a bird which uses this. So this is using contact angle hysteresis to your advantage. In a wedge-like geometry, you can drive drops towards the mouth of a bird.
Are these videos, do you have videos here multimedia field, whatever?
That's what this is from.
I know, but are some of these videos yours?
Yes, that one's not actually mine, but I think it's Debbie Carre's. I'm not sure. But yeah, this was first. This mechanism was first elucidated in our study of birds. Yeah. Okay, very good.